welcome back to the final week, week 12 of the problem solving session for the Introduction to Fluid Mechanics course. And in this week's session, or in this final session, we'll be dealing with one of the very important applications of fluid mechanics in our day-to-day life, primarily used in various engineering applications, that is flow through pipes. Okay, and flow through pipes, or the design of pipes to get the optimum flow rate or getting the least head loss, has been one of the crucial challenges for engineers for a long time, and creating better piping systems and pipelines, or piping piping junctions has been one of the very important topics of research in the domain of engineering, specifically in the domain of mechanical engineering or civil engineering. So we'll be dealing with flow through pipes in today's session, and we will also be briefly dealing with dimensional analysis, which is again a very crucial tool, as I can say, in the domain of fluid mechanics, as it helps us to understand the or I can say understand a way to find the solution of governing equations by considering the terms that have higher order magnitude or have more importance than the other terms in the governing equation. So for example, in the case of flow over flat plate or boundary layer flows, for example, there are certain terms in the governing equations, this is specifically the Navier-Stokes equation, that are predominantly insignificant compared to some other terms because of their higher order magnitudes. And in order to have that idea of how a particular term in the governing equation scales, the idea of dimensional analysis is very crucial. Moreover, today's session will primarily be concerned in understanding the parameters, or understanding the group of dimensionless numbers that govern a particular problem, and those the way of finding those non-dimensional numbers or non-dimensional parameters is done through the help of the Buckingham pi theorem. So we'll be dealing with that also, and that's basically the content or agenda for today's session. So let's begin with that, and I hope I am clearly audible. So if you have any doubt, you can stop me in between, or else you can just revisit the lectures by Prof. Chakraborty and put your doubts or queries in the discussion forum. Okay. So we are dealing with the flow through pipes, and that kind of flows, or those kind of flows have an exact solution. That is, flow through pipes or the is also popularly known as the Hagen-Poiseuille flow, is one of the exact solutions of the Navier-Stokes equation. Exact solutions in the sense that we are able to find a closed form analytical solution of the entire governing equation. By the entire governing equation, I mean that we start with the entire governing equation, but we cancel out the terms that become mathematically insignificant because of the chosen assumptions, or moreover, by the essence of dimensional analysis, we can cancel out the terms from the governing equations, so that we are left with a very simple one-dimensional ODE that we can solve to get a closed form solution of the given problem. And for flow through pipes, that kind of flow is known as the Hagen-Poiseuille flow. Okay, so let us consider this particular geometry. So let us consider a flow through pipe flow through an inclined pipe, which is inclined at an angle of theta, which has a radius of capital R, and say has a length of L. Okay. So I guess in the previous in the last week's session we were discussing briefly about developing region and fully developed flows. So we also consider a fully developed flow through a circular pipe or a tube. Okay. So in the case of fully developed flow, as I was mentioning, for flow through pipes or even flow through two parallel plates, the boundary layer merges after boundary of the flow merges after a certain length, and that length, say LE, is known as the developing length. Okay, and that region that is comprised within the length of LE is known as the developing region. Okay, and the flow beyond the developing region is known as a fully developed flow. So in the sense of simplifying the calculations or analysis, we will consider a fully developed flow. Okay, and the main difference is that in the case of developing region, for this kind of flows, the velocity is function of, or the velocity is a function of R and Z. Okay, but in the case of fully developed region, the velocity is function of R only. Okay. So to solve the given problem, we take the usual approach of mass and momentum conservation. So let's begin with mass conservation. So we deal with the continuity equation first, which is dou rho by dt plus nebula dot rho v is equal to 0. Okay, and see, this is the vector form of the equation, but as I mentioned in the previous sessions that the vector form of equation is universal, so it is applicable for any kind of geometry, but the form of the equation that we are going to write, or the when we want to write the equation in its component form, then it is then when where we need to understand that which coordinate system is more applicable or more suitable for this for the given problem in hand. Okay, since in the case of flow through parallel plates, the geometry allowed us, or the geometry, according to the geometry, we were it was more suitable for us to use the Cartesian coordinate system. So similarly, in the case of flow through pipes or cylindrical pipes, the cylindrical coordinate system seems to be much more relevant compared to other coordinate systems, that is the spherical or the Cartesian coordinate system. So it's not that we cannot do that, but it's highly illogical or difficult to approach a problem from the essence of Cartesian coordinate system to deal with a type of flow that is having a cylindrical geometry. Okay, so in the case of pipes, the cylindrical coordinate system is the one that is considered to be ideal and understood to be, and it's a very general practice to solve this kind of problems, flow through pipes problems, using the cylindrical coordinate system. So we will adhere to that. So keep having that idea in mind. So we will write the governing equations or the components of the governing equation in the cylindrical coordinate system. Okay, but since the continuity equation is a single equation and does not have any components, so we write it in the terms of the cylindrical coordinate system, or cylindrical or velocity components in the cylindrical coordinate systems. So you can write that dou rho by dou t plus 1 by r dou by dou r rho r v r plus 1 by r dou by dou theta rho v theta plus dou by dou z rho v z. Okay, and we take some assumptions for solving the problem. First, we take that the flow is axisymmetric. Okay, so for axisymmetric flows, we will have dou by dou theta is equal to 0. Okay, so since dou by dou theta of any property is 0, so this term will go out. So we will be left with, and we can also consider the flow to be steady, so this term will also go out. Then we are left with this term and this term. Again, since we told that the flow is fully developed, that's why the velocity component along z direction is only a function of r. Okay, so this derivative of this partial derivative with respect to z will also cancel out because of the fully developed flow assumption. I'm not saying that Vz is 0, but this entire derivative dou by dou z of Vz is 0 because of the fully developed flow assumption. That's why we will have 1 by r dou by dou r of rvr equal to 0. Okay, and there's one more key thing to consider is that axisymmetric flow does not ensure that v theta is 0. Like the theta velocity component is 0 in the entirety of the flow. It doesn't ensure that, but it just ensures that the theta velocity component is not a function of theta. Okay, But the assumption that we take in this case is that the problem has no stored velocity. That basically means that the v theta component of velocity is 0. Okay, that we explicitly take this assumption. Okay, that's why v theta is 0. But if we only tell that the flow is axisymmetric, we cannot say for sure that the v theta component is 0. Okay, it only tells us that the v theta component is independent of theta. Okay. Now, since we have that dou by dou r of rvr is equal to 0, rvr is equal to 0, it basically means that rvr is not a function of r. Okay. So from the boundary conditions, we'll have that from no penetration boundary condition, we'll have that at r equal to r, vr is equal to 0. That is the radial component of the velocity, vr is 0. Okay. And since vr is 0 at r equal to r, basically at this edge and this edge, it basically means that vr is equal to 0 for all r except at r equal to 0, which is a singularity case. Okay. So just one second. And that's why we can tell that vr is not a function of r. Okay. Just one second. uh, just one second. So from the continuity equation, we got two conclusions that uh, vz is not a function of z and vr is 0 for all r. Okay. So from the theta component of the momentum equation, we can write, see again, this form of the governing equations in different coordinate systems will have slightly different from. Okay, the general or the canonical structure of the governing equations will remain the same, but depending on the coordinate systems used, we'll have some additional terms in the cylindrical and the spherical coordinate system, mainly because of the fact that the different coordinates that we are choosing are not independent of each other. Okay, the details I don't want to mention in this session, but just to say that since the coordinates are itself not independent of each other, that is basically the r component or theta component are not independent of each other in the case of cylindrical coordinate system. That's why there are some additional terms in the governing equation that arise because of this dependency that we also need to take into consideration. Okay, so so it's in general, it's usually not a, what to say, or a necessity to remember by heart the entire form of the governing equation, because those are already given in the standard books, and usually any professor that is going to take the fluid mechanics course will usually encourage the students to have a problem, to have a, say, equation sheet that has the entire governing equation. Okay, because this equation in itself is a very, to remember the entire form of the equation correctly, since uh, the very number of terms in the equation are very large, so it's very difficult to remember each and every term in the governing equation. So it's usually a general practice by most of the professors who is going to take the fluid mechanics course to allow the students to have a problem sheet that contains these governing equations. But the more important thing that we need to learn is to apply those equations for a particular problem, and then understand which terms we can cancel out by applying the correct assumptions for the given problem. Okay, so that is what's more important and more necessary, rather than remembering each and every term or form of the terms in the governing equation, because that's just something that can be done by anyone. But understanding how to apply those equations for a given problem, first of all, like what kind of form of the governing equation will take, what form the governing equations will take according to the given problem in hand, and what are the assumptions that we need to take to simplify the problem, and depending on those assumptions, what are terms that will get cancelled out from the current equations. Okay, so these are three things that we need to emphasize more rather than learning the equations by heart. Okay, but again I'm saying it's not a bad thing to know the equations, but that's not the most important thing. Okay, that's what I wanted to mention. Okay, so keeping that thing idea in mind, so from theta component of the momentum equation, we will have rho dou v theta by rho t plus vr dou v theta by dou r plus v theta by r dou v theta by dou theta plus vr v theta by r plus vz dou v theta by dou z is equal to minus 1 by r dou p by dou theta plus mu dou by dou r 1 by r dou by dou r v theta. I guess this is better. Plus 1 by r square dou square v theta by dou theta square plus dou square v theta by dou z square plus 2 by r square dou vr by dou theta plus rho b theta. Okay, and you can see there are some term cancelled out from the ground equations. I will tell why. See, we took an assumption that v theta is 0 in this given problem, that is there is no swirl in the given problem, right? So that basically means v theta is 0 in all the terms, so that's why we'll have the first term is 0 by the assumption of a steady flow. Then the second term vr is also 0, but v theta is also 0, so both cancel out the term. Then again v theta is 0, so this term will go out. Again v theta is 0 in this term, so v theta will go out. Again v theta is 0. Okay, basically all the velocity terms will go out because v theta is 0, so this is 0, this is 0, this is 0, this is 0, and we are left with rho b theta and 1 minus 1 by dou p by dou theta. Okay, moreover we also took an assumption that since the flow is axisymmetric, all the properties with respect to theta would be the derivative of all the properties with respect to theta would be 0, so dou by dou theta of p would also be 0, so we are only left with that rho b theta is equal to 0. Okay, so there is nothing, the only conclusion that we get from the theta momentum equation is that rho b theta is 0, or the body force term along the theta direction is 0. Okay, that's what we get. We can just also write it in a small text there. Okay, now from the r momentum equation we will get rho multiplied by dou vr by dou t plus vr dou vr by dou r plus v theta dou vr by dou theta minus v theta square by r plus vz dou vr by dou z would be equal to minus dou p by dou r plus mu dou by dou r 1 by r dou by dou r r vr plus 1 by r square dou square vr by dou theta square plus dou square vr by dou z square minus 2 by r square dou v theta by dou theta plus rho vr. Okay, see, you can clearly see there are some additional terms that arise in the ground equation that are not explicitly present in the Cartesian coordinate system. For example, this term, then this term. So these terms are not usually present in the Cartesian coordinate system, but since there is a coupling between the r and theta coordinates in the case of the cylindrical coordinate system, so these are the additional terms that arise that we also need to take into consideration. But fortunately these are 0 in this case, but still depending on our problem, say if there is no swirl, they say, then this term will again be non-zero, right? So if the flow is not axisymmetric, then this term will also be not 0, so we need to consider these things. Okay, but for the given problem we have that v theta is 0, dou by dou theta is 0, and vr is 0 for all r. Okay, so keeping that idea in mind, so we'll have vr, this term will go out because the flow is steady, plus vr is 0. Again this term will go out because vr is 0. This term will go out because both v theta is also 0, vr is also 0. I'm sorry, this term will go out because v theta is 0, and then this term will go out because vr is 0. vz is not 0, but vr is 0. Okay, then we will have again vr is 0, so this term will go out. We will have vr is 0, this term will go out. Again this term will go out. Then again we will have v theta is 0, so this term will go out. Okay, so the only thing we are left with in this equation is that minus dou p by dou r plus rho br equal to 0. Okay, now br is, if we just let me just go back to the initial diagram. If you look here, then the body force along the r direction would be g cos theta. Okay, br would be minus g cos theta. Okay, and along the z direction it will be minus g sin theta. Okay, keeping in mind that if we take this as positive r and this as capital positive z, then it will be minus br, minus br will be minus g cos theta, and bz will be minus g sin theta. Okay, so let me go back to our momentum equation. Okay, so from that we will have that dou p by dou r will be equal to minus rho g cos theta. Okay, so this is the conclusion that we get from the R momentum equation. And finally, the most interesting component would be the z component, because flow is primarily along the z direction. That's the most interesting component of the Gaussian equation. Similarly, in the case of say flow through parallel plates, is that the x momentum equation is gives a very what to say, proper idea of the flow, and is primarily considered to be the most interesting component, because most of the term it is the equation that retains most of its term. Similarly, in the case of flow of parallel plates in a boundary flow, it is the x momentum equation that retains most of its term, and it is the equation that we are eventually going to solve. But the y momentum equation also gives us a very good idea about the terms that are what are the terms or terms that cancel out, and we also use the, in the case of boundary flows, the implication of the y momentum equation is also observed in the x momentum equation. Okay, I'm not saying they are not important, but the primary equation in consideration is primarily the direction along which the primary flow occurs. Okay, so just 1 second again. Okay, so from this we will have, from the z momentum equation we will have that, let's consider the z momentum equation first. That we will have rho multiplied by dou vz by dou t plus vr dou vz by dou r plus v theta dou vz by dou theta plus vz dou vz by dou z would be equal to minus dou p by dou z plus mu 1 by r dou by dou r dou vz by dou r plus 1 by r square dou square vz by dou theta square plus dou square vz by dou z square plus rho bz. Okay, you can see here that there are no additional terms in the z momentum equation, because the z component, the z coordinate is independent of theta and r in the case of cylindrical coordinate system. So the additional terms do not arise in the z component of the momentum equation. Okay, so now let's see what are terms that you can cancel out. It is already cancelled out in this equation, but I will tell you why they are cancelled out. Okay, so from the first term, since we know that vz is not 0, right, so we need to know why these terms are getting cancelled out. Okay, so the first term is cancelled out because the flow is steady. The second term is cancelled out because vr 0, dou vz by dou is not 0, but vr is 0, that's why this term gets cancelled out. Then again, the second thing, v theta is 0, but dou vz by dou theta is not 0, is also 0 because the flow is axisymmetric, but v theta is 0, so this term gets cancelled out. This also cancel out the term. So finally we will have vz by dou vz by dou z. So vz is non-zero, but dou vz by dou z is 0 because the flow is fully developed. Okay, so this term is 0, so we are left in the right hand side. Dou p by dou z should exist because we don't know how the pressure varies along the z direction, so there is a pressure dependence. Moreover, since we already knew that dou p by dou theta is 0, so, and dou p by dou r is non-zero, so there has to be and moreover, since pi flows are pressure driven flows, there has to be pressure component or the variation of pressure along the direction of the flow. Okay, so this term, at least in the case of pi flow, can never be 0. Okay, moreover, by the means of rigorous mathematical analysis, that also this term is not 0, but logically speaking also this term has to be non-zero because the flow is along the z direction. Okay, and that's why there has to be a pressure gradient along that direction to have a primary flow in that particular direction, right? So this term can never be 0, okay, logically speaking, but through mathematical rigor also you can tell it's not zero, because there's no assumption still, there's no assumption that has been made yet that can nullify this term from the governing equation. Okay, so that's why this term is non-zero. Okay, then for next terms we'll have this term is again non-zero because dou vz is function of r because of the fully developed assumption. So since vz is not a function of theta because of the axisymmetric assumption, and vz is not a function of z from the continuity equation, so we'll have that vz is function of r. Okay, the next term, this term will get cancelled out because vz is not a function of theta because of the axisymmetric assumption. I'm sorry if I'm going a bit fast, so let me just again repeat it, that vz is a function of r because vz is not a function of theta because of the axisymmetric assumption, and vz is not a function of vz is not a function of z because of the continuity equation. So that's why we're left with fully developed assumption. So vz is the function of r. So this term will be non-zero, and we are left with the body force term along the z direction. Okay, so this will exist. So now if we take into account all the remaining terms, the governing equation that were left in hand is dou p by dou z is equal to mu 1 by r dou by dou r plus r dou v z by dou r is minus rho g sin theta. Okay, because the body force along the z direction is minus rho g sin theta. Okay, as can be seen from this diagram. Okay, so from the r momentum equation we have that 0 is equal to minus dou p by dou r minus rho g cos theta. Okay, now if the pipe is really thin or the radius of the pipe is much smaller than the length of the pipe, then this body force component can ideally be neglected. Okay, because the variation of pressure along this length would be almost negligible compared to the variation of pressure along this direction because of the length of the pipe. Okay, because of the pressure gradient that exists between the two ends of the pipe that causes the flow. Okay, so the pressure gradient along the radial direction would be essentially very small if the radius of the pipe is much smaller than the length of the pipe, which is usually the case in the case of pipe flows, right? Because the length of the pipe is much longer than the radius of the pipe. That's why this component of the body force can ideally be neglected in the r momentum equation. So from that we will get that p dou p by dou r is equal to 0, which will essentially tell us that p is not a function of r. Okay, this is also an assumption that we are taking, an approximation that we are taking, but which is as good as it gets. Okay, that's why it can be considered to be an exact solution. Okay, so p is not a function of r. So since p is not a function of theta or r, then but p exists in the flow, that's why p is a function of z only. Okay, so that's the first thing that conclusion that we get. Now if we look into the z momentum equation, so the terms that we're now, if we look here, okay, let's look here itself. Since p is function of z only, so this partial differential can be converted into a complete differential dp by dz, right? And moreover, since vz is function of r only, just one second. Just one second. Okay, apologies for the delay. So now, okay, yeah, as I was mentioning, that since p is only function of z, then this partial derivative can be converted into a complete derivative, right? So it will become dp by dz. Okay, again from this from the z momentum equation we get to know that since z is not a function of z, vz is not a function of z because of the fully developed condition, and vz is not a function of theta because of the axisymmetric condition. So vz is only a function of r. Okay, so this partial derivative can also now be converted into a complete derivative. So once we do that, we can write this z component of the momentum equation as dp by dz plus rho g sin theta is equal to mu 1 by r d by dr r dvz by dr. Okay, something that I already wrote here. Okay, so now if we club together this term into one single term, so we will have, if we consider p star is equal to p plus rho g z sin theta, and then z sin theta would be equal to, basically would be equal to h. Like if we go back to the if we go back to this diagram, okay, this is let me just draw it here, that is a little more clear. Say this is the pipe, right? This inclined pipe, and say this is, I'm zooming it down here. Okay, so we're left with theta here. So this is z, then this z sin theta, and this will be z cos theta, right? Then z sin theta will basically imply the vertical height. I go back, I'm sorry. Then z sin theta will basically imply the vertical height through which the variation of pressure is going to take place. So z sin theta will be equal to the vertical displacement of the fluid. Okay, so keeping that idea in mind, so we can write p star is equal to p plus rho g z sin theta will be equal to p plus rho g h. Okay, which basically tells us this is the piezometric pressure. Okay, piezometric pressure, considering the total the pressure variation along with the pressure variation because of the height difference, okay, or hydrostatic pressure difference as well. So if we write p star is equal to p plus rho g z sin theta, so we can club them, these two terms together, into single term to write dp star by dz is equal to mu 1 by r d by dr r dvz by dr. Okay, and this is the final from the ground equation that we are going to solve. Okay, now again, similar to something that we already did in the previous session, in the case of flow between two parallel plates. Now dp star by dz is only a function of z, okay, because p is not a function of r or theta. Similarly, mu 1 by r d by dr r dvz by dr is only a function of r. Okay, and since these both of these terms are functions of different uh, independent coordinates, and thus in order to have this equation, or in order to have these terms equated, both of them have to be equal to a certain constant c. Okay, now that's why, similar to what we did for a float between two parallel plates, we can first consider the right hand side. So let me consider this term to be equal to some constant c. Okay, then we will have d by dr r dvz by dr will be equal to c by mu r into r. Okay, then r dvz by dr will be equal to, if we integrate it once, we will have c by mu r square by 2 plus c1. Okay, and now if we take r here, then we will left with dvz equal to cr by 2 mu is plus c1 by r. Okay, and now if we integrate it again, we will have vz is equal to cr square by 4 mu plus c1 ln r plus c2. Okay, so now we have two boundary conditions, because this is a second order. If it is second order in r, then we will need to have two boundary conditions to solve this equation. So we will have r is equal to, at r equal to capital R, we will have vz equal to 0 because of no slip boundary condition, and moreover at r equal to 0, vz is finite. Okay, vz has to be finite at radius equal to 0. Okay, which gives us the symmetric boundary condition. Okay, so imposing these two boundary conditions here, so by imposing the second boundary condition, c1 ln r will be equal to 0, c1 will be equal to 0. How? Let's go back two steps before. Okay, so from this equation, if we integrate it once, we are left with r dvz by dr is equal to c by mu r square by 2 plus c1. Okay, now if we take r equal to 0 here in this equation, this term will be equal to 0, right? and this term will also be equal to 0 if dvz by dr is finite, right? So if that's finite, then since r equal to 0 and here this term is also equal to 0, then we are left with c1 is equal to 0. Okay, so this tells us that the first constant c1 is 0. Okay, or just the constant, because first constant is c, that is the constant term which these two derivatives are equal to. So c1 is 0. Then from the no-slip boundary condition, if we apply now the equation that we are left with is basically Vz as a function of r is c r square by 4 mu plus c2. Okay, so now if we apply the second boundary condition, that is, so the first boundary condition, that is the no slip boundary condition, we will be left with at r equal to capital R, Vz is 0, so this term is left hand side is 0, so cr square by 4 mu plus c2 is equal to 0. Then c2 would be equal to minus cr square by 4 mu. Okay, now if you substitute the value of c2 in this equation, we will get Vz is equal to cr square by 4 mu minus c capital R square by 4 mu. Okay, now if we take minus cr square by 4 mu common from this both the terms, we will left with Vz as a function of r would be equal to minus cr square by 4 mu in bracket 1 minus small r square by capital R square. Okay, and now we know that c is equal to dp star. Let me just write it, okay, to do better, so that you have a clear idea. Now we know that so now we know that c is equal to dp star by dz. Okay, so now from this equation, we see here is that there is a minus sign in front of c. Okay, so now in order to have, and moreover we also know that small r is always less than or equal to capital R. Okay, so this term can either be 0 or less or greater than, this term has to be positive because r is either less than or equal to 0. Okay, so this term has to be positive. Okay, so now, and r is positive, 4 mu is positive, so only term that can change the sign of this equation is this term c. Okay, where we know c is equal to dpz by dp star by dz. Okay, so now in order to have a positive value of vz, you can clearly see that this dp star by dz has to be negative, because if there is negative, then this minus sign will cancel out that negative sign, then we will have a positive value of vz. Okay, and that's why, as I have written here, dp star by dz has to be negative to drive the flow in the positive z direction. Okay, and that's what it's the concept of the existence of a favorable pressure gradient. Okay, so moreover, in this term favorable pressure gradient is usually used in the case of flow over flat plates or flow over airfoils, where the favorable boundary conditions accelerates the flow, and the presence of adverse pressure gradients decelerates the flow and in fact results in flow separation. Okay, but similar concept or idea can be imposed here also. So if there is a favorable pressure gradient that is going to drive the flow in a positive z direction, it will basically mean that if I draw a pipe here, say, then this point 1 and point 2, then to have favorable pressure gradient, we need to have P2 less than P1. Okay, the pressure at the exit must be lesser than the pressure at the inlet, so that it can drive the flow in the positive z direction or any positive Cartesian coordinate direction. Okay, so I'm sorry, any direction. Okay, z to z, that's what this is a coordinate system that we are mentioning, but I'm saying at any direction, in order for flow to have positive, in order to have the flow occur in the positive direction, we need to have a pressure at the exit to be lower than the pressure at the inlet to have a negative pressure gradient, because by negative in the sense we can clearly say that the pressure is decreasing as we are moving forward in that particular coordinate direction. Okay, So that's what we have here, the governing equation or the final form of velocity profile in the case of flow through pipes. Okay, so this is the form of the velocity profile. Okay, so uh, we can wait here for 2 minutes so that you can digest and cross check all the derivations that we have discussed till now, and then we can go ahead with the remainder of the derivations and the problems in hand. Okay, so we can stop here for a few minutes and then we can start again. Okay. Okay. Again, sorry for the delay. So let's continue now. Okay. So we have the final form of the velocity profile in our hand. Yes. Let me just write it once again. So the final form of the velocity profile is given by Vz of r is, let me just write it properly. So V0 of r is equal to minus c r square by 4 mu 1 minus r square by r square, where c is equal to Vp star by Vz. Okay. So now we see the we try to find the average we try to find the average velocity of the flow through the pipe. Okay, in order to find that, we again just equate the uh, volume flow rate through the pipe using initially by using the general integration, since the velocity of the flow is changing, uh, sorry changing with respect to r throughout the cross section of the pipe, so we cannot just directly use a single value of velocity for evaluating the volume flow rate, and thus we need to take the aid of integration. Okay, so but if we assume that there was a that if we are able to equate the volume flow rate through the pipe by using a constant value of velocity through that particular cross section, then we can conceptualize or find the value of the average velocity through that particular cross section. Okay, so what I'm basically trying to mean is that let me just write it here. Say the volume flow rate through the pipe by like in ideal case would be given by 0 by r vz of r, say, into 2 pi r dr. This is the volume flow rate. Okay, now if I am saying that, let us say that I am trying to consider this volume flow rate should be equal to the area of the pipe times a constant value of velocity. Okay, just say that the value of this volume flow rate is, I am trying to equate it by finding the product, or by equate it to a product of the area of cross section of this pipe and a constant value of velocity, which is not equal to, say, VR max or anything, but it's a value something in between. Okay, 0 to the maximum velocity. Okay, so that would be that would mean that would be equal to, say, or this is the terminology I've used here, is equal to v bar into pi r square. Okay, since the radius of the pipe is capital R, then area is pi r square, so v bar into pi r square should be equal to this volume flow rate. Okay, then it would basically mean that v bar would be equal to, or the average velocity would be equal to, integration from 0 to r vz 2 pi r dr, where 2 pi r dr is, sorry, 2 pi r dr is the elemental area in the cylindrical cross section divided by pi r square. Okay, so this is exactly what I have written here. Okay, so once you cancel out pi from both the terms and take out 2 and r square, so we can write v bar is, or average velocity, equal to 2 by r square integration from 0 to r vz into r dr. Okay, now if we substitute the value of vz in this equation, then we can find the expression for v bar in the case of, or average velocity in the case of, flow through pipe. Okay, so now let's just substitute the value of VZR in this expression and try to evaluate the integration. Okay, so if we substitute this in this equation, we will have, let's write it, simplified it, so you can write that v bar will be equal to 2 by r square integration of 0 to r minus c r square by 4 mu 1 minus small r square capital R square into r dr. Okay, so again this r square will cancel out, this will cancel out, so we will left with minus c by 2 mu integration from 0 to r 1 minus r square with capital R square. Sorry for the mistake, just want to write it properly. Okay, so now you can understand how it's obtained. So once you multiply r with this term in the bracket, we will be left with v bar is equal to minus c by 2 mu integration from 0 to r minus small r cube by r square. Okay, so once we evaluate the integration, we will get that v bar would be equal to minus c r square by 8 mu. Okay, so you can check the integration. Oh, I'm sorry. So you can check the integration in these two steps. So after you do that, we'll get that v bar equal to minus c r square by 8 mu. Okay, and to find c would be equal to minus 8 mu v bar by r square. Okay, now if we substitute the value of so now if we take the ratio of v bar and vz, because vz is this and v bar is now v bar is c minus c r square by 8 mu. So if we take the ratio of that, we'll get that vz by v bar will be equal to 2 in bracket 1 minus small r square by capital R square. Okay, here which tells us that the velocity profile in the case of flow through pipes is a parabolic velocity profile with respect to r. Okay, see, you can even tell that from the initial profile also. VZR is minus CR square 4 mu 1 minus R square by R square, because C is a constant, R is a constant, 4 mu R constant, and capital R square is also constant. So only term that is varying is small r square. Okay, so from here also you can clearly tell that it's a parabolic velocity profile, and thus this parabolic shape of the velocity profile. Okay, with respect to r. Okay, so that's can easily be understood. But still, the more important essence or more important conclusion that we get from this equation, that clearly tells us that if from the you can find here the concept of maximum velocity. Okay, so at r equal to 0, vz would be maximum, right? That can also be observed. Let me go back in this diagram as well, that at r equal to 0, the value of the velocity, value of the z component of the velocity would be maximum. Okay, so from here, if we substitute r equal to 0, so we will get vz by v bar is equal to 2 or I can write, let me write it in this way, so it is, you can refer the notes again. Vz would be equal to Vz max. Okay, so it will mean Vz max by V bar is 2, or the maximum velocity Vz max is equal to 2V bar. Okay, or the value of the maximum velocity in the case of a pipe flow is 2 times its average velocity. Okay, again that's a very important conclusion. So these kind of statements or relations are asked in many competitive exams such as GATE or ESE. Say 1 mark question also, but it's fine. But if you remember the relation beforehand, like in the case of pipe flows, the maximum velocity is 2 times the average velocity, or in the case of flow to parallel plates, the maximum velocity is 1.5 times the average velocity. So having that idea in mind, you can, if you already know it beforehand, so you need not go through the entire derivation once again, but just remembering the statements, because you've already done the derivations previously, it will be very helpful to get score marks, good marks in those for a particular question in those exams. Okay, so now let's find the expression for the wall shear stress in the case of flow through pipes. Okay, so to find the expression for wall shear stress, we again you take the aid of the Newton's law of viscosity. From that we know that tau is equal to mu 2 mu Eij. Okay, Eij is the linear strain rate. Okay, so if you substitute that here, we will get that tau wall at Rz is equal to minus mu v dou Vz by dou R plus dou Vr by dou Z at R equal to R. Okay, and we use a negative sign here because the positive r direction, that it is r, points towards the wall from the center line, okay, in the opposite sense, okay. So keeping that idea in mind, we can write, and moreover in this equation we will have that Vr equal to 0, because we found that Vr equal to 0 for all r except at r equal to 0, okay. So that's not happening here. We are not considering the case here now, so we are only considering the stress at the wall. So we are essentially 0 at the wall as well, right? Because because also from the boundary conditions, right? For no penetration boundary condition, Vr is 0 at r equal to r, okay. So for having that idea in mind, but what's more important here is that Vr is 0 for all r, okay. So even if wall shear stress is even though it only exists along the wall, and we are trying to get that value here, but this Vr equal to 0 is 0 for all r, okay. 0 for all r except at r equal to 0, okay. So having that sense, we can write we can cancel out Vr from this term, okay. And that's we're left with tau wall rz would be equal to minus mu dou vz by dou r, okay. So once you substitute the expression for vz for r small r equal to r, you will get that tau wall at r equal to r would be equal to 4 mu v bar by r, okay. It's a very simple substitution. Just substitute the value of this expression in this equation. So r equal to capital R, so it will basically give that, sorry, just let me just show you, okay, that will be much better. So we can write Vz equal to 2v bar 1 minus r square by capital R square, okay. Now we need to substitute dou Vz by dou r, okay. So this will imply dou Vz by dou r would be equal to minus 2v bar into 2r by r square, okay. So basically give us minus 4v bar r by r square. For r equal to r, this will basically give us minus 4v capital R by capital R, okay. So now, sorry, I am extremely sorry, it will give us minus 4v by capital R, okay. Now since there is a minus mu multiplied here, so we will get that tau r at r equal to r would be 4 mu v bar by capital R, okay. And now to find the coefficient of friction, it will basically be the ratio of the wall shear stress by the kinetic energy. So basically the ratio of wall stress by the fraction of the by the kinetic energy, which is corresponding to the average velocity. So from that we will get that Cf would be equal to 8 mu by rho Vr, okay. So if you modify this term again, so because if we I'm sorry, so this term will give, if we modify it, if we convert r into the diameter d, then just multiply 2 to both the numerator and denominator, we'll get Cf is equal to 16 by mu rho Vd, or 16 by Red, where Red is the Reynolds number with respect to the diameter of the pipe, okay. So and this friction factor is known as the fanning friction factor, okay, related to the wall shear stress, okay. Now let us consider this equation, okay. dp star by dz is equal to minus 8 mu v by r square, okay. So again this is obtained from the from the initial boundary equation, because if I go back here, we got that C is equal to minus 8 mu v by r square, which is equal to again dp star by dz. Okay, so if we take that equation in mind, we can write dp star by dz is equal to minus 8 mu v bar by r square. Okay, now since dp star by dz is equal to a constant c, it basically means that this p star is a linear function of z. Okay, so we can write dp star by dz is also equal to p star out minus p star in divided by L. Okay, a linear function of z. Okay, so we can write it. You can write, basically it means that pressure varies linearly along L. Okay, now we substitute this in this equation. We will have p star out minus p star in divided by L is equal to minus 8 mu v by r square. Okay, now in the case of, if this pressure drop, okay, or this pressure variation is primarily because of the viscous resistance, okay, then we can write this pressure variation, that is p out by minus p in, as the pressure variation because of the viscous resistance, which would be equal to hf into rho g. Okay, or where hf is the loss of head due to fluid friction. Okay, so this is, we can write p in minus p out is equal to hf rho g, because p in is greater than p out. Why? Because since there is a pressure head loss because of the fluid friction, so p in must be greater than p out. Okay, so we can write delta p star, or this as hf into rho g, or minus hf into rho g, because p in is greater than p out. Okay, so if we substitute this here, we can write hf into rho g by L equal to 8 mu v bar by r square, or 32 mu v by capital D square. Just substitute r by d by 2, so we will get hf rho g by L is equal to 32 mu v by d square. Okay, now we know that v bar is q by pi d square by 4. Okay, because we wrote that q would be equal to average velocity into the area. Okay, so v bar is volume flow rate by area. Okay, so again rho g hf would be equal to 32 mu ql by pi d square by 4 into d square. Okay, just substitute v bar by this to get rho g hf is equal to 32 mu ql by pi d square by 4 into d square. Then finally we can write rho g hf is equal to 128 mu ql by pi d to the power 4. And finally, if we substitute, if we take rho g into the denominator, we can write hf is equal to 128 mu ql by rho g pi d to the power 4. Okay, and this equation is known as the Hagen-Poiseuille equation. Okay, that gives us the head loss due to friction factor in terms of the experimentally measurable quantities, because mu is something that is already known in the case of any fluid, pi is again a constant, d is something that is already known for a particular diameter, and q is something that we can usually find by doing certain experiments. Okay, so once you do that, so once that is found, we can easily find the value of hf from this equation. Okay, the head loss in a pipe from this equation. Okay, now we can represent hf. You can also represent hf, or the head loss due to friction factor, in the terms of the fraction of kinetic energy head. Okay, because why the fraction of kinetic energy head? Because since there is a loss in the flow energy because of the fluid friction, so we can basically tell that this head loss hf would be equal to some fraction of the total kinetic energy head. So we can write hf is equal to f into L by d v square by 2g. Okay, so these terms are non-dimensional, but this term is dimensional because it is the kinetic energy head. Okay, now if we equate this to equation number 1 here, then we can write FLD into v bar square by 2g is equal to 32 mu v bar L by rho g d square. Okay, then if we cancel out the terms and rewrite the equation, we can write F is equal to 64 mu by rho v d, which is basically equal to F equal to 64 by RED, or which is the Reynolds number with respect to the diameter of the pipe. Okay, and this is F, this F is known as the Darcy's friction factor. Okay. Now see, there's again a very crucial relation here. Okay. First is that the first friction factor that we initially found, that is CF, is the fanning friction factor that is related to the wall shear stress, and the second friction factor that we found, that is F here, is actually the friction factor because of the head loss due to the fluid friction. Okay, and since you can see that since F is 64 by RD and CF is 16 by RED, so the basic relation that we get here is that F is 4 times the fanning friction factor, or the Darcy friction factor is 4 times the fanning friction factor. And as it is mentioned here, and as it also mentioned in the lecture Professor Chakraborty, that this relation is bound to happen. Why? Because since the flow has to overcome a wall shear stress for the flow to occur in the particular direction, and it is the presence of this wall shear stress that results in the pressure drop in the case of flow, in the case of the flow through a particular pipe or channel. Okay, and since these physical phenomena are inherently related to each other, and that's why the friction factor that we found out by two different concepts. Okay, first is by the wall shear stress. Of course, they are inherently connected by the origin, but the origin through which these were found by are different. First was found through the wall shear stress, and second was found by the concept of fluid friction or head loss in the case of pipes. Okay, and since these two physical phenomena are inherently related, that's why these two friction factors are also very elegantly related to each other, where we can say that Darcy friction factor small f is 4 times the fanning friction factor CF. Okay, and the pumping, and just again a equation to know, a equation that comes handy is the pumping power required to overcome this head loss in pipes is given by rho g HF into Q, or delta P star into Q, where delta P star is the piezometric pressure difference. Okay, because of the head loss. Okay, so let me just go through some basic formulas. Again, I will not go through the entire derivation. These two I have already dealt with, and up to this I guess, but other two I won't go deep. I will just tell you the formulas, and you can just revisit the lectures of how they were obtained and know the relation, and then you can find out. Then we can use them in the solution that we are going to use them in the problems that we are going to study in today's session. Okay. Okay, then let me just quickly go through the problems, or quickly go through the formulas. So this is that these two we have already dealt with. HF is equal to FL V square by 2GD. So this is Darcy-Weisbach equation, or the Darcy friction factor. Sorry, Darcy-Weisbach equation, and F is the Darcy friction factor. And HF is also equal to 128 mu QL by rho g pi d to the power 4. This is the Hagen-Poiseuille equation. Okay, this is a very important equation. That one, if you remember, like you can easily solve problems related to pipe flows. Okay, and those are quite simple. Like those equations, all the value of the parameters are given. You just need to remember the equation to find the head loss. Okay, given that they have mentioned that it's a fully developed flow through a pipe. Okay. Then the equation of pumping power is also given. So H is the friction head loss due to friction, and H is the vertical height that the flow needs to be pumped from one reservoir to other reservoir. So the pumping power required would be the vertical height, the sum of the vertical height as well as the head loss due to friction. Okay, so that will be the net pumping power required. Okay, then DH is the hydraulic diameter, which is basically given by 4A by P, where P is the weighted parameter. Okay, say if this is the pipe and flow occurs through the entirety of the pipe, then the weighted diameter is the entire circumference of the pipe. Okay, weighted perimeter. I'm sorry. Then for hydraulically smooth pipe, friction factor F is equal to 0.316 by RED to the power 0.25, which is valid for okay, now one more important concept to keep in mind, which is valid for Reynolds number varying from 4000 to 10 to the power 5. Okay, so the important concept that I guess forgot to mention here is that all these formulas, okay, not all these formulas, actually these are valid for turbulent force as well. No, sorry, I'm extremely sorry. So this cannot be, because this is inherently found by taking into assumption that okay, then I need to cross verify, just forgive me for that. But the important thing is that this friction factor, the equation of friction factor F is equal to 64 by ID is only valid for laminar flows. Okay, so this formula for friction factor is only valid for laminar flows, and is only valid for Reynolds number less than 2300 for pipes. Okay, similarly this formula also, that defining friction factor, if I go back, that Cf is equal to 16 by ID is only valid for laminar flows, where ID again is less than 2300. Okay, and for finding the friction factor in the case of, and okay, just now I recall. Now even if the expression for the friction factor, like this, F by 64, F is equal to 64 by ID is valid for only laminar flows. Okay, but this equation, that head loss is equal to F in FLV square 2GD, is valid for turbulent flows as well. Okay, so the only thing that varies in the case of turbulent flows is the value of the friction factor. Okay, and to find the value of friction factor, we take the aid of a very famous chart or diagram known as a Moody's chart or Moody's diagram, and there we can find the value of friction factor, where the friction factor now depends on Reynolds number as well as the surface roughness of the pipe. Okay, so which is usually represented by epsilon by d. Okay, the surface friction, sorry, the surface roughness. Okay, so so there is a formula for, so here they have given a formula for hydraulically smooth pipe, for where the flow for turbulent flows as well, we have a formula for the friction factor. But a usual practice is to take the aid of Moody's diagram to find the value of friction factor in the case of turbulent flows. But since they already mentioned your formula here, you can use that. But the more ideal practice is to use the value of to find the value of the more ideal practice to find the value of friction factor F is to take the aid of the Moody's diagram. Okay, so that we have not discussed here, but something that you can look into. Okay, and finally there is the concept of kinetic energy correction factor, which is basically the ratio of the kinetic energy flux evaluated using the actual velocity, that is say u in this case, and the average velocity, and the kinetic energy flux obtained by using the average velocity. Okay, so this is the relation through which the kinetic energy correction factor can be obtained. And in the case of circular pipes, this is the closed form equation. Okay, so because u by u bar you will know, because it's basically, again, if I'm not wrong, it's 2 1 minus r square by capital R square, if I'm not wrong, right? So u by u bar in the case of pipe flows is 2 1 minus small r square by capital R square, right? So let me just go back to verify. Yes, Vz by V bar is 2 multiplied by 1 minus small r square by capital R square. Okay, so since there's the relation, so from that you can easily find the value of kinetic energy correction factor alpha from this relation. Okay, now, so now we are left with three important topics. So again, this topic I will not go deeply, because this was very properly discussed by Professor Chakraborty in the lectures. That is the junction of pipes, that is pipes in series and pipes in parallel. But the important concept that you need to keep in mind are the fundamental idea of behind the uh, uh, connection of pipes, okay, or the junction of pipes, okay. So in the case of pipes in series, the important thing to keep in mind is that the volume flow remains constant through all the pipes, okay. So I say in the case of these two pipes, the volume flow rate Q will remain constant, okay. But the head loss in these two pipes will be different, and the net head loss through this pipe would be actually the sum of the two head losses in these two separate pipes. This HF would be equal to HF1 plus HF2, okay. Now since we know that the volume flow rate remains constant through both the pipes, so we can take the aid of now the Darcy friction factor. So from that we know that HF is equal to FLV square by 2GT, okay. Now again we know V is equal to Q by pi D squared divided by 4, okay. Now if we substitute that this value of V bar in this equation, we will get that HF is equal to 16 FL by 2G pi square into D to the power 5, okay. See, now the thing is that say that you are going to say get an equivalent pipe that can be replaced by these two junction of pipes, okay, these two separate pipes, okay, these two pipes in series, okay. Say you want to get an equivalent pipe, say something that has a greater diameter compared to this and a lesser diameter compared to this, so having say an equivalent length LE and a equivalent friction factor FE, because FE is not constant for both the pipes, okay. So let's say we are getting an equivalent uh, uh, pipe having an equivalent length LE and equivalent friction factor FE, okay. So if you are going to replace this pipe, and in order to have the same volume flow rate, we take we substitute the value of HF in these equations, to get that 16 FE into LE by 2G pi square D 05, where and equivalent diameter say DE, okay, where FE is the equivalent friction factor of the new pipe that we are going to replace, that we are going to use to replace these two pipes in series, and LE is the equivalent length of the pipe that we need to have, and DE is the equivalent diameter of the pipe, okay. So HF would be equal to 16 FE LE by 2G pi square D 05 would be equal to 16 F1 L1 by 2G pi square D1 to the 5 plus 16 F2 L2 by 2G pi square D2 to the power 5, okay. Then if we cancel out the constant terms, that is 16 and 2G and pi square, we are left with FE LE by D to the power 5 would be equal to F1 L1 plus D1 to the power 5 and F2 L2 D2 to the power 5, okay. Say since there are only two pipes in series here, now if we consider there are n number of pipes, say, then we can write it as a summation of these terms. So FE LE by D to the power 5 would be equal to summation of from I equal to 1 to n Fi Li by Di to the power 5. Basically it will mean that F1 L1 divided by D1 to the power 5 plus F2 L2 D2 to the power 5 plus, let me write it properly, okay. Say it will be equal to F1 L1 D1 to the power 5 plus F2 L2 D2 to the power 5 plus F3 L3 D3 to the power 5 plus dot plus Fn Ln Dn to the power 5. This is what basically the summation sign means, okay. So let us go back, let me try to say create an analogy between this pipe junction of pipes and electrical that's the word I was missing actually, this pipe circuits and electrical circuits. Okay, so if we try to create an analogy between say electrical circuit having resistances in series and a piping network having pipes in series, so we can create an energy between the electrical concept and the mechanical concept here. Okay, so in the case of electrical circuit, if you are trying to find an equivalent relationship or analogy, then the current I can be considered to be equivalent or similar to the volume flow rate, and the potential difference between the circuit or between the resistances or between the two ends of the circuit can be considered as the net head loss. Okay, so this is what I have written here, that head loss would be the potential difference and the flow rate would be the current. Okay, that's why for pipes in series we'll have the same current or the same volume flow rate as mentioned here, and the net potential difference between between all the pipes would be the sum of all the potential difference, or in this case the sum of all the head losses. Okay, so similarly in the case of pipes in parallel, you can get that the potential difference V would remain the same, but the current or Q would differ from pipes to pipe or resistance to resistances. Okay, so similarly, like if you look into here, then in the case of resistances, the current is different in all the three branches of the resistances, but the potential difference is the same. Okay, in the case of electrical circuits. Similarly, in the case of flow through pipes, the volume flow rate is different for both the pipes, but the net head loss, that is HF, is constant for both the pipes. Okay, and moreover the relation is there. Here, since there are three circuits, the net current is equal to the sum of all the current through these different junctions. Similarly, the sum of the volume flow rate is equal to the sum of volume flow rate through these two different junctions. Okay, so the equation that we have in our hand is Q is equal to Q1 plus Q2, that is the total volume flow rate is equal to sum of volume flow rates through these two separate pipes, and HF1 is equal to HF2. Okay, where HF1 is the head loss to the first pipe, the HF2 is the head loss to the second pipe. So HF1 is equal to HF2. Moreover, since if we are going to separate, if we are going to substitute this parallel piping circuit by a equivalent pipe having a friction factor Fe, a length Le, a diameter De, and a head loss HFE, which would indeed be again equal to HF1 and HF2, then we can write that 16 Fe into Le by into Q square divided by 2g pi square d to the power 5 would be equal to 16 F1 L1 Q1 square divided by 2g pi square d1 to the power 5 is be equal to 16 F2 L2 Q2 square divided by 2g pi square d to the power 5 will be equal to some constant k. Okay, then we can write, if we just substitute, if we just take this 16 2g pi square as some constant c, say, then we can write Q1 square would be equal to k d1 to the power 5 by c f1 l1. Okay, so we just write it so you can write it for one case so you can understand. Okay, so 16 f1 l1 q1 square by 2g pi square d1 to the power 5 is some constant k. Okay, then if I consider 16 by 2g pi square as some constant c, okay, then we can write c f1 l1 q1 square by d1 to the power 5 is equal to k. Okay, or q1 is equal to square root of k d1 to the power 5 by c f1 l1. Oh, sorry, L1. Then we can basically write similarly for Q1 equal to Q2. This would basically mean square root of k d1 to the power 5 c f1 l1 equal
equal to square root of k d2 to the power 5 c f2 l2. Now since k and c are constants, we can neglect this, cancel out this term, so we will left with square root of d1 to the power 5 by f1 l1 is equal to square root of, we just write it once, it's not proper, d2 to the power 5 f2 l2. So something that I written here. Okay. So I'm sorry. That's why I was saying it's not right actually. So if I let me write it properly. So, let me just write it. Okay, I'm sorry for the mistake. So we know that q is equal to q1 plus q2. Then q would be some constant, say k, some equivalent diameter de to the power 5 by c f e l e. Okay, would be equal to the sum. So since k is constant and c are constant in all the terms, we can cancel out that. So we can write de to the power 5 f e l e would be equal to this. Okay, so that's something that's already written here. Okay. So this is the relationship between for pipes in series and pipes in parallel connection and series connection. But there is a something that it's good if you remember, but something that you can easily obtain if you know the concept. Okay, so that's something. I leave it up to you. If you want to remember, that's fine. But if you don't remember, also just know the equations that you need. That is, for pipes in parallel, Q is equal to Q1 plus Q2, and HF1 is equal to HF2. And for pipes in series, you will have Q1 equal to Q2, and HF is equal to HF1 plus HF2. Okay, so that's fine. So the final concept that we have in our hand is the concept of dimension analysis, as I was mentioning. So again, I will not go deep into it. It's a very extensive topic to discuss. Like, it has lots and lots of what to say, in detailed explanation and concepts in hand. So that is something that can only be understood if I was going to give a lecture on a single lecture or 2-hour lecture on dimension analysis itself. But since I'm saying that this is something that is a part of today's session, so I'm not going to extensively discuss about it. I'll very briefly go through the fundamental concepts of similarity that is already shown in the screen. That's fine, but I won't go or dive deep into the each and every detail of the explanation or derivations. Okay, so it's something that I expect you to do. But again, if you have any doubt, you can once again just go back to the lecture by Prof. Chakraborty. So they will give a very proper insight of these fundamental concepts of dimension analysis, or say geometric, kinematic, or dynamic similarity, how the concept of similarity comes into picture, where are the points of application of this similarity, and why to understand, first of all, why to study this similarity or dimension analysis. Okay, so that's something that you can if you want, you can learn by looking at the lectures, and it's a very extensive and beautiful topic actually. But for the sake of saving time, I won't go back to each and every detail of this concept here in today's session. Okay, so in dimension analysis, there is again a concept of prototype and a model, where prototype is actually a has a scale or has a length scale of something that we are going to experiment upon, the same length scale of something that we are going to experiment upon, and model is a miniaturized or rescale version of the same prototype. Okay, so in order to have total similarity, we need to have these three similarities. We need to satisfy these three similarities. Okay, so a model and prototype is said to have a geometric similarity if there is a similarity in the geometry. Basically, the length scales or the ratios or the ratio of the length scales of the geometry in a prototype should be same. So this, then we can say that the geometry that the prototype and the model has a geometric similarity. Then in the case of kinematic similarity, you need to have a similarity in motion. There is a value of the velocities in different points of the prototype or the model should be in the same ratio. Okay, and finally, for to obtain dynamic similarity, the net forces that act upon the model and the prototype should be similar. Okay, not the same obviously, but similar in the sense that there must be a scaling between the forces that act upon. There must be similarity in the scaling of the forces in the model and the prototype. Okay. Then in order to uh, have a quantitative approach to dimension analysis, there was the inclusion of the Buckingham Pi theorem, which basically states that if a given problem in hand, like if we are going to analyze the or understand the problem through dimension analysis, that we are going to understand which are the non-dimensional numbers or non-dimensional parameters that can be used to define the problem. Like if I'm going to say that, say the flow through flow over a flat plate, so this kind of flow depends on, say, the inertial, sorry, the incoming free stream velocity, or the length scale of, or the length of the plate, okay, or the viscosity of the fluid. So these are the parameters through which over which the problem is based upon. Okay, but again, these parameters can again be clubbed together to a non-dimensional value. Say if we have the kinematic viscosity nu. Okay, let me just write it. Okay, so in the case of flow over a flat plate, yes, funny enough, I got a very elegant example to tell. So say in the case of flow over a flat plate, so this kind of flow is not a boundary layer. So this kind of flow would, by looking into it itself, you can check the parameters that you have in your head. Okay, so it will depend upon the incoming free stream velocity. Okay, because that's the parameter that can be changed. Okay, that is in our control. Then we can use you can change the fluid that we are going to use. So we have the control of the kinematic viscosity of the fluid. Moreover, we can also have the control over the length of the plate we are going to use. Okay, so say up to this point, we have the length of this plate is x. Okay, say we are going to find the velocity profile or flow parameters at a particular length in the plate. Say then this is the length x, say, that varies from this is the length of the distance or a point from the leading edge of the plate. Okay, so now this problem you can clearly see now depends on three different parameters. Okay, but through dimension analysis you will get to know that all these parameters, if clubbed together, can be represented in terms of a non-dimensional number. This is basically the local Reynolds number of the flow. It is u infinity x times nu. Okay, this is a non-dimensional number that could define all the physics or problem that we are going to obtain by clubbing together these parameters into a single non-dimensional number. Okay, there is a Reynolds number, local Reynolds number in the case of flow over a flat plate. Similarly, there can be different problems that would have much more parameters that we need to control, but again those parameters can be reduced or reduced to have a better understanding, and those parameters can be substituted, or sorry, those parameters can be replaced by some fewer number of non-dimensional parameters or non-dimensional numbers. Okay, so the Buckingham Pi theorem states that if there are m physical parameters in a particular flow, and there are n fundamental parameters. By fundamental parameters, I mean the scales. That is, say in the case of velocity, velocity is comprised of length and time scale, right? So fundamental parameters would basically mean the fundamental scales that comprise all the parameters in the flow. Okay, say pressure would again be a scale of mass, length, and time. Okay, but the fundamental parameters is the mass, length and time itself. Okay, so in most of the physical cases is usually these three, but say if there is temperature involved or there is energy transfer involved or heat transfer involved, then again the fundamental scale will involve, since it will involve the thermal conductivity, then it will have a temperature scale as well. So temperature will also be a fundamental parameter. Okay, but usually for most of the fluid flow problems, if it is not dealing with say heat transfer, it's usually the mass, length and time. Okay, so there are three fundamental parameters usually, but I'm not saying those are only ones. In general, I guess they have 7 fundamental parameters, but depending on the problem, the number of fundamental parameters can change. But for most of the fluid mechanics problem that we're going to deal, the fundamental parameters that we will have in hand will usually be 3. Okay, so then the Buckingham pi theorem states that the problem in hand can be represented as a function of m minus n non-dimensional parameters, okay, which are known as the pi terms. Okay, so this is the Buckingham pi theorem. So we'll take one example to get into it, but let's go through it. Let's go to the problems once. Okay, so again, today's problems are very simple. Since we are already running late, I will just try to go through the questions as fast as possible, so that you can just pause it and rewind it to take the solutions. But let's just try to see it. Okay. Okay, so you can just wait for once. Okay, so I just forgot to download the problem sheet, so you can just go back and download it. Okay, so you can kindly wait for 1 minute. So okay, so let's go to the problem once. Let's go to the problems in our hand. So the first question is that consider a pipe that branches out into 2 parallel pipes. Okay, and then rejoins at the junction down the downstream. The 2 parallel pipes have the same lengths and friction factors. The diameters of the pipe are 3 cm and 6 cm. If the head loss in the 3 cm pipe is 0.64 meter, then the head loss in the other pipe is, so it's a very extensive question, but it has a very simple answer. So there's a trick is in the pipe of the junction type of junction that is mentioned here. Okay, so you can go to the question once again, and you can see for yourself how simple the answer is. Okay. So here you can clearly see that they mentioned that the piping junction is actually a parallel junction. Okay, parallel junction or parallel connection. Okay, so this is mentioned here. So if they are mentioning that the head loss in the 3 cm diameter pipe is 0.64 meter, it would inherently mean that the head loss in the 6 cm pipe would also be the same. That is 0.64 meter, because the very concept of having a parallel connection is that the head loss in the 2 junctions are exactly in the 2 pipes are exactly the same. All the pipes in the junction is exactly the same. So that's why the head loss in this case would be 0.64 meter. Okay. So the next question is, 2 pipes of identical length and material are combined in parallel. The diameter of pipe 1 is 4 times the diameter of pipe 2. Assuming the friction factor and the pipe length to be the same in both cases and disregarding the minor losses, find the ratio of flow rates in 2 pipes Q1 by Q2. Okay, so you can pause the video here to revisit the question, but since that for sake of saving time, I would directly like to go and show you the solution. Okay, and you can just cross verify it once you're able to write all the parameters and check it. Okay, so let me just go back. Okay, so this is the solution that I have written. So I mentioned that diameter of pipe 1 is 4 times the diameter of pipe 2 in the junction, and the friction factor and the length of the pipes are the same. Then we are asked to find the ratio Q1 by Q2. Okay, so just one second. So we know that in the case of parallel connection, the net flow rate is equal to the sum of the mass flow rates, the volume flow rates, Q1 plus Q2, and the net head loss in both the pipes are the same. Okay, so I will not go back and revisit the formulas once again, just for your understanding. I have written the formula. So we have that HF1 is equal to HF2. Okay, so we will have, you can directly go here. Then we will have 16 F1 L1 by Q1 square, F1 L1 Q1 square by 2G pi square D1 to the power 5 will be equal to 16 F2 L2 Q2 square divided by 2G pi square D to the power 5. Okay, then we can cancel out the constant terms to get that F1 L1 Q1 square by D1 to the power 5 equal to F2 L2 Q2 square by D2 to the power 5. They are equal. Okay, and now since we already know that F1 is equal to F2 as mentioned here, and L1 is equal to L2, then we can write Q1 square by D1 to the power 5 will be equal to Q2 square by D2 to the power 5. Then if we take the ratio of Q1 by Q2, we will have Q1 by Q2 will be equal to D1 by D2 to the power 5 by 2. Since D1 by D2 is equal to 4, then we can write Q1 by Q2 is equal to 4 to the power 5 by 2, which will basically give us Q1 by Q2 is equal to 32. Okay, so the correct answer in this case will be 32. Okay, so next question is, pipe A is connected in series to another pipe whose diameter is twice the length. Pipe A is connected in series to another pipe B whose diameter is twice and length is 8 times of pipe A. They mention the relation here. If both the pipes have the same friction factor, the ratio of frictional head losses for pipe A to those of pipe B, HFA by HFB is given by. So we need to find. Similarly, we need to now we're doing pipe in series. So let us go through the problem once. So they mentioned that diameter of pipe B is 2 times the diameter of pipe A, and the length of pipe B is 8 times the length of pipe A. And friction factor at both the pipes are equal. Then we need to find the ratio of HFA by HFB. Okay, so we know that for the pipes in series, the net head loss is actually the sum of head losses in the two separate pipes. Then again, this formula I won't write again, but we can just revisit the formulas that we already discussed and cross verify. Okay, then we will have 16 FE Q square by 2G D05 pi square will be equal to 16 F1 L1 Q square divided by 2G D1 05 pi square plus 16 F2 L2 Q square divided by 2G D2 05 pi square. Okay, now if we cancel out the constant terms here, we will have FE by D to the power 5 equal to F1 L1 D1 to the power 5 plus F2 L2 D to the power 5. Okay, now we are asked to find the ratio of HFA by HFB. Okay, so for that I don't think you need to have this calculation in hand, so you can just disregard it. Since you already know the expression for HFA and HFB separately, you can just take the ratios. So but for that you need to, since as I mentioned, you do not always know that the expression for the head loss explicitly. So so from here also you can just tell that for HFA would be FA LA by DA to the 5 and HFB would be FB LB DB to the 5. Okay, so just take the ratios. So we will have HFA by HFB would be equal to FA LA by DA to the 5 and FB LB DB to the 5. Okay, now since FA and FB are equal as mentioned here, then we can cancel out both these terms. So we will have LA by LB, HFA by HFB will be equal to LA by LB into DB to the 5 by DA to the 5. Okay, and just substitute the value of LA by LB and DB by DA. So we will get 1 by 8 into 2 to the power 5. So from that we will get 32 by 8 will be equal to 4. So we will have HFA by HFB equal to 4. So the correct answer in this case would be C, is 4. Okay, so now we have a interesting question. It's a very there are 5 questions plugged in together. So let us go through the question slowly. Okay, so the question is, a rotodynamic fluid machine of a given shape and handling compressible fluid, the relevant variables involved are d, the rotor diameter, q, the volume flow rate through the machine, n, the rotational speed of the rotor, gh, the difference of head across the machine, energy per unit mass, rho, the density of the fluid, mu, the dynamic viscosity of the fluid, and the P is equal to power transfer between the fluid and the rotor. With the help of Buckingham's pi theorem, the relationship between the variables can be expressed by a functional form of the pertinent dimensional parameters as f pi 1, pi 2, pi 3, pi 4 is equal to 0. Okay, so they're basically telling us that there are 4 non-dimensional numbers here. Okay, the number of fundamental diameters in which the variables can be expressed is equal to c. Since we have 7 non-dimensional 7 parameters in the given problem and 4 non-dimensional numbers, so the value of fundamental parameters would basically be since we know this say capital, so m minus n will give the number of say pi terms, right? So since let me just write it here, I'm going to go back there. So m minus n is equal to pi terms. Okay, so this is 7, this is n, and this is sorry, and this is yeah, it's correct, and this is 4. So n will basically be 7 minus 4, that will be equal to 3. So correct answer is A. As I already mentioned, since this kind of problem is not dealing with heat transfer, so for most of the fluid mechanics problem, the number of fundamental dimensions is usually 3. Okay, so first correct answer is 3. So second question is, if pi 1 is q, or if pi 1 is q rho a1 and n b1 d c1, then the value of a1 b1 c1 are okay. So so they have also given us a hint of the repeating parameters to be chosen. So repeating parameters that they are going to choose are the density of the fluid, the number of rotation, the rotational speed of the rotor, and the diameter of the pipe. So if you recall, Professor Chakraborty mentions that this choice of repeating variables should be such that they themselves do not form a non-dimensional number. Okay, so that's very important thing to observe. So any ratio between rho, n, and d should not form a non-dimensional number themselves. Okay, so that was something that we need to focus upon. But in this given problem, they've already given us the repeating variables or repeating parameters. So that's something that comes in very handy. So they've told that pi 1 is q rho n rho a1, n b1, and d c1. Okay, so let me just give you show you one of the examples, and I guess you can go through all of them yourselves. So that will be much more better, much more better for you. Okay, so let me just go through this example once. Okay, so for the first non-dimensional parameter, let me just write it. So we have that pi 1 is q rho a1 n b1, and this I have not written one here, that's fine. So the dimensions of d is L, n is time inverse, and rho is ml to the power minus 3. Okay, so q, the dimension of q also we know is lq by lq into t to the power minus 1. Then we have ml to the power minus 3 into a to the power a, t minus 1 to the power minus 1 to the power b, and l to the power c. And once you equate this parameter, once you equate this powers, once you equate these powers, we'll have L 3 minus 3a plus c, t to the power minus a minus b, and n to the power a. And since we know all these parameters have the value of 0 in this right hand side, because this is equal to 1 basically, because it is dimensionless, so we have the a would be equal to 0. Okay, so we have got a equal to 0. Then minus 1 minus b equal to 0, so b will be equal to minus 1. And if you substitute the value of a here, we will get c equal to minus 3. So pi 1 would be q n dq. So if we look back in the problem, so a is 0, b is minus 1, and c is minus 3. So the correct answer is c. Okay, so let us take one more example. Pi 2 is g h rho a2, n b2, and d c2. Okay, find the value of a2, b2, c2. So if we look back here, again same steps, gh rho a, n b, rho to the power a, n to the power b, d to the power c. GH would be L square D to the power minus T to the power minus 2. Rho A would be ML minus ML to the power minus 3 to the power A, T to the power minus 1 to the power B, and L to the power C. Again, equate all the take common all the powers for the similar bases. Then L would be equal to L to the, then for L it would be L to the power 2 minus 3A plus C, 2 minus 3A plus C. T would be minus 2 minus 3A, sorry, T would be equal to minus 2 okay, I have a mistake here, I guess. So it would be not minus 3A here, so it will just be minus L2 is minus 2 and minus B, and L is T and M is to the power A. Okay, so since A is equal to since this all are equal to 0, this M, let me write it here once, M to the power 0, L to the power 0, and T to the power 0. So since both sides are equal, then from dimensional similarity, or from the principle of dimension homogeneity, we need to have both the powers of this side, all these terms should be equal to 0. Okay, so we'll have A is equal to 0, A would be equal to 0 here. Then B would be equal to minus 2, because minus B minus 2 is 0, then B equal to minus 2. And if we substitute the value of A and A here, A and A here, from that we get C equal to minus 2. So from there we will get pi 2 is equal to GH by n square into d square. Okay, so I think that's all I will do. That these two only I will do, I guess. Others, okay, let's do the last one. Okay, so last one says that pi 4 is P rho A to the 4 and B to the 4 and D C to the power 4. Then find the values of A4, B4 and C4. Okay, so again, since these are repeated, I didn't want to repeat, but just say for the sake of understanding, let's do the final one again. Okay, so for power, we find the dimension of power as this. So we get the dimensions of power as ml squared t to the power minus 3. Okay, it's again a very good practice. Like if you sometimes you do not know the exact expression for the sorry, you do not know the exact dimensional expression for any given parameter, then you can just dissociate it into some other fundamental parameters, right? Then since we know power is force into velocity, then we can write, and since we know the dimensions of force and velocity, we can just multiply it to get the dimensions of power. Okay, so something that I myself done here. So the dimensions of power is ml squared t to the power minus 3. Density is ml to the power minus 3. T is for n is it is t to the power minus 1, and for d is l. Again, use the similar steps. Then take all the powers in common. So we will have m to the power 1 plus a, l to the power minus l to the power 2 minus 3a plus c, and t to the power minus 3 minus b. From that we will get, since a this all are equal to 0, since then we will get a is equal to minus 1. Since the sum of the powers in all these terms are equal to 0, we will get a equal to minus 1, b equal to minus 3, and if you substitute the value of a here, we will get c is equal to minus 5. Okay, so pi 4 will be p divided by rho n cube d to the power 5. So if you look here, okay, let me check. It is c is minus 5, b is minus 3, a is minus 1. So the correct option is D. Okay, so I guess that's all from my side for today's session. I hope I was able to. It was a very interesting session today because it was highly dependent upon the application part. Moreover, I also got to know about got to learn about dimension analysis. So that's again very an interesting topic or interesting tool in hand for any fluid mechanics expert or an engineer. So again, I will just encourage you, all of you, to go back to the lectures by Prof. Chakraborty, understand the concepts in a much more better way, and then try to solve more problems related to the topics that you discuss in a particular week, to get a proper idea or proper understanding of the problem, okay, or of the concept. So I guess that's all from my side today, and I wish you all of you all the best for your exams, and I hope I was able to help you out to understand even a bit, to help you to understand the concepts taught by Professor Chakraborty in the class, and help you out by understanding the help you out by help you out to solve the problems related to those concepts. Okay, so that's all from my side. So thank you, and